Hello class, so this is part of the video notes, so I do want you to try the problem first. These are some equations I thought you might find useful. If you need to write them down, I would pause the video now and write them down. So as far as this is the entire work problem, so try it first and then I will go over it piece by piece. So this is just practice. These are going to be your essentially one dimension because it's only going to move in one dimension, but you will have to know all parts of the force body diagram. So pause it, try it, and then we will continue. So for example, you first thing draw a really good free body diagram. So here is the free body diagram. It is a shoe on Earth, so there is some force of gravity. The elevator is accelerating downwards, so that actually will tell you that the normal force has to be a little smaller so it can accelerate downwards. And then if you draw a free body diagram of the shoe, it's being dragged by its laces horizontally. We don't really know which way, it doesn't matter. I am going to say that it's being dragged this way. I'm just going to call it an F push. And that, it's a carpet, there's definitely some friction going on. So in space, technically, our thing is actually going to be moving in this direction. It's going to go down and across. We'll talk more on that later. So based on this, what's the weight issue? Right, so the weight, remember, weight is the same thing as Fg. Or the force of gravity. So the force of gravity is the mass times the acceleration of gravity, or m times a, like every force equation. And we know that this shoe is 1 kilogram. Makes it easy. And the force of gravity has not changed, so it's still going to be 9.8 meters per second squared. Multiply all that up, and you're going to get 9.8 newtons. And since this is down, you would call it technically negative. So what is the normal force on the shoe? This is definitely a more complicated question. So we have the force of gravity, but we don't know the normal force because the normal force has to be different because it's currently falling. It has a downward acceleration. So this is the tricky part. You have to figure out what the net force is. So what is the net force? And we're talking about the up and down, so the y direction. What is the net force? The net force is going to be equal to the top, the up, the normal force, minus gravity. How can we know what the net force is? Well, the net force of this is also equal to the up minus the down, as well as the mass times the acceleration in the y direction. Do we have an acceleration in the y direction? Why, yes. Yes, we do. That is our 2 meters per second squared. That's our acceleration in the y direction, right? It's accelerating down. So this would technically be, again, negative. So our mass is, again, just 1 kilogram. So your net force is 1 times a negative 1. So your net force for this, y, is negative 2. I'm going to write into problem C. So our net force is negative 2 newtons. We don't know what our normal force is, but we do know that our gravity is 9.8 or 10 if we rounded. So given this, what does the normal force have to be for the overall force to be negative 2? So you get in alone, so you can solve it, or the normal force in. So you add 9 plus a negative 2, which will give you 7.8, or if you rounded, it would just be round to 8, is your normal force. So this is probably, I would think, this is one of the harder problems on here. As far as the math goes, you have to do a couple steps, but your normal force ends up being equal to the total force minus, or opposite, so you're technically adding your 9.8, which will give you 7.8 newtons. So I'm going to erase this so I can now have room for C. If you need it, just go back. Alright, so then we look at the elevator has a carpet that has a mu of 2. What is the force of friction? So we already found the normal force, right? Our normal force was 7.8 newtons, or remember 8 newtons if you rounded your gravity. So what's the force of friction? Force of friction is equal to mu times the normal force. And we know the normal force, and it told us mu. So this is as plug and chug as it sounds. Your mu is 2. Your normal force, I'm going to simplify to 8 really quick. So your normal force was 16 newtons. That was it. Your normal force is 16. That's actually a really large force on it. But shoe on carpet does have quite a bit of friction. You don't want to be slipping and sliding. So if, given that it's moving horizontally at a constant velocity, so this is, remember, if we refer back to our free body diagram, gravity is slightly bigger than the normal force, because normal force is only 8, gravity is 10 newtons. But we're now saying that, okay, so our friction is huge, which is 16 newtons, and that our force of tension, it's moving constant. So we know that, hey, if it's moving constant, that means the F of x, or the sum of the force of all of x, ends up being equal, right? Because it's not accelerating. Constant velocity, remember, always know constant velocity means no acceleration. No acceleration. And if no acceleration, that means there's no force. No acceleration means no force, or no sum of forces, no net force. So if there's no net force, what has to be the force of tension? I wrote it as force pull. It should have been force tension because laces, you're pulling on the laces. What would be the force of your tension? Hopefully you can think, well, okay, if you had to pull 60 on this, you also have to pull 16 newtons on your tension. So your force of tension would also be 16 newtons. That is a really sticky floor, by the way, and really sticky shoes. But hopefully that proved insightful, so this would be solving it where your net force would just be 2 newtons down, because I said, oh hey, if your tension was greater and you were accelerating, but we're not. So we're just falling down with a force of 2 newtons if you were to subtract all of these out. Alright, hopefully that was enlightening. We will do one more together, and then you are done with your homework for tonight. So this is number 4 from your packet from what we did on Wednesday. So you are pushing a box horizontally across your driveway. As always, make a free body diagram first. So you're pushing a box horizontally. Friction also acts on a box. So you push it with a force, so this is your F push, with 13 is equal to 13 newtons. There, however, is friction, but your box does accelerate. It is also on Earth, so there is a force of gravity going on here, as well as a normal force. So given the fact that it accelerates at 0.5 meters per second squared, how do we then find the friction? So it doesn't give you the overall mass of the box, so we can't necessarily find friction the traditional way of finding the normal force and then solving for friction with mu, because we don't know that either. The key point here is that we do know how much it accelerates. So what you're going to have to do is set up a couple different problems. So it's the idea that the net force of your x is equal to your right minus your left, and the net force that was a terribly written sigma. The net force of your x is also equal to the mass times the acceleration in that direction, which we do know. So for here we go, okay, well, I know what the right is, right? It's 13. So we can fill that in. So the 13 minus the left, which is what we're trying to find, we know it's equal to, we don't know the mass, but we do know the acceleration was 0.5 meters per second squared. And actually, I realized I did forget to write something in, because I was like, that's really hard. Like, how would you solve it? So if you tried to solve it and you're like, that's impossible, how do you solve it? You're right. Given the way it's written, it's pretty much impossible, given your current level of knowledge of physics, to solve that. So scratch some of these things. I apologize again. And I am going to give you the mass of your box. So let's say your mass is 2 kilograms. So if you tried it, go back now, try it, see if you can solve it now with the 2 kilograms. Alright, so you are going to need the mass of the box to solve this. So let's now, this force diagram still works, but now we could theoretically figure out what Fn and Fg are equal to. So for example, Fg is the same as the mass times the gravity. Your mass is now 2 kilograms. I'm going to round and use the 10 for the gravity. So both your normal force, because they are equal, and your gravity force are going to be worth 20 newtons. And then again, it's the same idea that we know two things about the sum of the forces in the x direction. One is that it is the right minus the left, which is 13 newtons minus the force of friction. And we also know that the box accelerates in the direction we push it, which would be to the right, depending on the way you drew the problem. And then we know that the mass is equal to the force is equal to the mass times the acceleration. And we do know the mass, so it would be 2 kilograms times 0.5 meters per second squared. A relatively light box. So it's only accelerating a little, so 2 times 0.5 is 1 newton. So your total net force is only 1 newton. Given that, how big is your friction? So we can go back in and plug in 1 for our total force, 13 newtons for that, and for our friction force. So to solve this, we need to get friction alone. So you subtract by 13 by both sides. So you get negative 12 is equal to your friction force. So the friction force backwards, since the net force is 1, the force going in the opposite direction of your force of 13 would be 12. And I'm going to do a quick little extra bonus thing. So now that you know that, what would be mu? So now we can go back and take, okay, so our friction was 12. We want to find mu. And we know that our normal force, because remember friction is equal to mu times our normal force. Our normal force was 20 newtons. So you can go back and divide 12 divided by 20 newtons will give you the mu. And if you plug that into your calculator, you get 0.6 is equal to the mu of your box. Alright, hopefully that was helpful, and I will see you all tomorrow.